We'll have 16 papers to be presented in this session. And the first paper is MIDI-VALLE, Improving Expressive Piano Performance Synthesis through Neural Codec Language Modeling. The presenter is Jingjing Tang.
So, hello everyone, I'm Jingjing Tang, and welcome to the presentation of our ISMIR paper. I'll be introducing MIDI-VALLE, an expressive piano performance synthesis model built on neural codec language modeling. This work comes from a collaboration project between Center for Digital Music, Queen Mary University of London, and the National Institute of Informatics in Japan. Our work falls within music performance synthesis, which focuses on transforming score MIDI into expressive audio performance. We usually consider it as a two-stage process. The first step is called expressive performance rendering. That's where we add expressiveness to the planned score and turn it into performance MIDI. The second step is expressive performance synthesis, or EPS, which takes this performance MIDI and turns them into realistic audio. Our study focused on optimizing the second stage to improve the overall quality and also the compatibility with the first stage models. So most existing EPS models for piano either build on differentiable digital signal processing, aiming to directly model the physics of sound production, or they adapt conventional text-to-speech model, treating MIDI to audio as an analogy to text-to-speech. Typically, these models generate spectrograms and use a vocoder to render the waveforms. While this approach can produce convincing results, there are still several limitations. First, they often don't generalize well. Switching to a new piano or a different recording setup or a new playing style can make the quality drop. Second, they give you limited control over details such like the piano tone, articulation, or resonance, which makes them less flexible. And third, in the two-stage pipeline, the mismatches in MIDI representations between the stages can introduce timing error and distortions, reducing overall synthesis quality. So to overcome these limitations, we adapt VALLE, a neural codec language model originally built for text-to-speech, to expressive piano performance synthesis. So first, we fine-tune the encodec model to compress and tokenize piano audio. This led us to train on larger and more diverse dataset to improving the overall generalization. And second, because it works with discrete tokens, we can align MIDI and audio more accurately, solving the mismatch issue that usually hurt two-stage pipelines. And third, we extend its zero-shot adaptation ability to piano synthesis. So with just a short audio clip, we can control the piano's tone and acoustics in the generated performance. So by adapting VALLE to EPS, we demonstrate that neural codec language modeling, which is already successful in many text-to-speech and many other audio and music tasks, can also produce expressive and realistic pianos from the MIDI. So here's how we adapt VALLE for our task, starting with this dataset. We use 8-tab dataset for training, compare with the more commonly used dataset, the Maestro, which has about 200 hours of piano competition recordings. 8-tab has over 700 hours and 10,000 recordings from multiple pianists, composers, and live settings. So it's better suited for robust neural codec language modeling. Then for the tokenization of the audio and MIDI, which contributes significantly to the success of the adaptation, we first fine-tune a variant of the encodec model originally used in the Music Jam paper on the 8-tab dataset. And we create what we call piano encodec. It uses residual vector quantization with 4 codebooks to describe these audios. This design allows us to reconstruct high-fidelity piano audio from discrete tokens. And for MIDI tokenization, we adapt the octuple strategy, where each note is described by multiple features. In addition, we include the inter-onset interval tokens to explicitly model the expressive onset timing, helping the model to capturing fine-grained performance nonsense. As for the model itself, we mainly follow the original VALLE design with minor changes to support MIDI tokenization. The model consists of an autoregressive transformer decoder and a non-autoregressive transformer decoder. The autoregressive decoder predicts the first codebook, and then the non-autoregressive decoder generates the remaining 3, conditioning on that first one. So finally, during the inference stage, these codebooks are decoded back into audio with our piano encodec model. We evaluate the model's performance on 3 datasets, the ATAP, Maestro, and Pajama. The Pajama dataset includes jazz performances with paired audio and transcribed MIDI files. In terms of the objective evaluation matrix, we measure FAD using embeddings extracted by piano encodec, which reflects overall perceptual quality and the timbral realism. We also calculate spectrogram distortion, which captures how well the acoustics and timbral are reconstructed. And finally, we calculate the chroma distortion to evaluate the harmonic consistency between the ground truths and the modal outputs. So from the table, we could see that our piano encodec model performs well across all 3 datasets, with much lower spectrogram distance and chroma distortion than the original encodec model. And for the synthesis quality, we compare MIDI-VALLE with a baseline called M2A, which was presented in ICASP this year. This baseline follows a conventional TTS design. A transformer generates the spectrograms, and hi-fi gain acts as a vocoder. So it was trained on Maestro and fine-tuned on ATAP. So in the table, all the matrices are computed against both the ground truth audio as well as a reconstruction from the piano encodec. So compared to M2A, MIDI-VALLE achieves more than 75% lower FAD on both the ATAP and Maestro datasets. On Pajama, which contains jazz performance, the FAD scores are still high, suggesting that jazz remains challenging, likely due to its different rhythms and harmonies. In terms of harmonic consistency, MIDI-VALLE performs similar to M2A on the ATAP dataset, but M2A does slightly better on Maestro, likely because it was trained there. And last, for the spectrogram distortion, the MIDI-VALLE is consistently closer to the reconstructions, meaning it better captures acoustics and timbral details across all the datasets. So the quality of our model can also be visualized by this rainbowgram. It uses colors to indicate frequency and lightness to represent the amplitude. This is calculated from the constant Q transform. We here compare an example of the MIDI-VALLE outputs with M2A model and the ground truth and the piano encodec reconstruction. By comparing the similarity of lightness and color in this highlighted area, you can see that MIDI-VALLE provides a more accurate reconstruction across all the full frequency. Finally, we conducted a listening test to subjectively evaluate the synthesis quality and system compatibility of our model. So from this left table, you can see MIDI-VALLE receives significantly more votes than M2A on ATAP and Maestro for synthesis quality, showing it adapts better to classical piano. However, on Pajama, M2A is slightly preferred, indicating jazz is more challenging to adapt to for MIDI-VALLE without any fine-tuning. And for system compatibility, we try to evaluate the quality of the outputs from the 2-stage pipelines. We feed output MIDIs from different expressive performance rendering models into the synthesis model. As the result shows, MIDI-VALLE consistently preferred over M2A when combining two different EPR models, showing that it could produce natural and expressive outputs more robustly. Now let me show an listening example to demonstrate the model's promising performance. I think it's loading, sorry. Maybe. Why it's not? Thank you. Okay, so you can scan the QR codes to hear more audio samples on our demo page. And you're also, where is mine? Okay. So you are also welcome to our poster session if your ears tired of more talking. So we will present a demo so you can listen to some samples. And I'm also happy to discuss more details and answer questions about this paper. So looking forward to seeing you there. Thank you.
Okay, next paper is titled Playability Prediction in Digital Guitar Learning Using Interpretable Student and Song Representations. It's going to be presented by NC Cloud.
I don't need the mouse actually, but yeah. Hi, I'm Anssi. I'll be presenting today because the first author unfortunately couldn't make it to the conference. The context of this work is the guitar learning platform that we develop at UCission. And the key idea of this paper is that we embed both students and songs into the same interpretable vector space, where the dimensions of the space correspond to different skills. And we use this to predict how well a learner will play a new song at the first try. So the motivation of this work is that online guitar learning is growing fast, but personalization still lags behind what a human tutor does, namely choosing the right material at the right time for a specific learner. Prior work in MIR has paid significant attention to modeling the song arrangement difficulty, but much less attention has been given to modeling the student. Our contribution here is twofold. We developed a student experience profile that captures what the learner has mastered. And secondly, we embed the students and arrangements into a joint vector space and show that this substantially improves the quality of playability predictions. To understand where the data comes from, here's the interaction loop of our platform. A student selects an arrangement and plays along with this interactive tablature. Our app listens to the student's performance and tracks them for pitch and timing accuracy. In order to fill this with meaning, we profile the song arrangements into interpretable musical features, such as rhythmic patterns, chord shapes, or technique-related aspects, as well as various difficulty estimates for both hands. The result is a compact representation of what the arrangement demands from the student. On the learner side, the student experience profile summarizes what the student has shown they can do on the platform over time. We increment the profile when the student performs a specific event correctly. So if you repeatedly nail a certain rhythmic pattern or chord transition, those dimensions on the skill profile are incremented. And because the dimensions are interpretable, they allow the system also to reason why a certain recommendation is given or why certain things are still hard for a user. In order to validate the quality of the embeddings that we are building, we chose the task of predicting the playability. That means the share of onsets within a song arrangement played correctly by the user. We did this because we analyzed explicit feedback of our users and discovered that the success ratio correlates quite nicely with the user sentiment, and that there is a sweet spot between like where the user is bored out and they are also not frustrated, but they are just like right in the zone playing with the song. When running predictive experiments with the gradient boosting model, we saw that both the embeddings of the student and the embeddings of the arrangement significantly outperform a weak baseline. But we see that the joint combination of the two does a much better job still, which is intuitive, because we want to know both about the difficulties of the arrangement as well as the mastery level of the student to match them. If this sparked your interest, I would be happy to chat with you and hear your thoughts on our poster. Thank you.
Next paper is Gregorian melody, modality, and memory, segmenting chant with Bayesian nonparametrics. The presenter is going to be Jen Hajic.
So, very quickly, how many of you have ever heard Gregorian chant? Oh, great. I don't have to explain what it is. Thanks. Yeah, maybe, but not after the keynote. So now for something completely different. Together with Wojciech Lanz, who unfortunately couldn't be here, we're digging into the deep medieval origins of European written music, the melodies of Gregorian chant. So this was the liturgical music of the entire Latin/Catholic Church for something like 1200 years. It actually stopped being official in 1970 something. And we have thousands of melodies like this in thousands of manuscripts. And the frustrating thing is we don't really know how these melodies are constructed. What we cannot do is apply our usual music theory, because even the term counterpoint is something like 500 years younger than this melody. So what we can do is take medieval theory, maybe, and we have modality. So mode is something that melodies are categorized into, so it works like a label. It's kind of like major or minor, but it's not only a label, it's also a practical way to group melodies according to similarity. But, well, this doesn't really explain how they are constructed, does it? So we have to guess. And one of these good guesses is centonization theory. It says that the melodies are built from some vocabulary of melodic gestures, and maybe modes could be sub-vocabularies. Chant scholars don't like this very much, but there are actually good reasons to expect something like that would happen. Most importantly, oral traditions tend to centonize as they get transmitted from one generation to the next. It's just easier to remember. If you have a melody that goes C, D, E, C, D, E, C, D, E, C, D, E, you just remember that as C, D, E 4 times, right? And chant is an oral tradition. For 300 years, it did not have exact pitch notation. You had to remember it. And afterwards, it was also not really sung from books. They're too small for groups to sing from. The problem is, to demonstrate that centonization works, you'd have to actually find it over a couple thousand melodies. And to demonstrate that it doesn't work, well, that's even harder, right? So here is where computational methods obviously come in. We come from the point that centonization makes sense if it helps remember melodies. We formalize this as minimum description length, which with the right distributions is equivalent to maximizing the posterior, so you just do Bayesian estimation. Specifically, for this task of unsupervised segmentation, there is available the nested hierarchical Pitman-Yor language model. So the Pitman-Yor process is the cool thing that makes this work for minimum description length, and you don't even have to specify the vocabulary size. The hierarchical part is how we make it model sequences, and nested means that we use an inner model over tones as a prior for the outer model over segments. This is a total monster, but fortunately you can sample from it just by counting things, which is why this is tractable. So we take the largest available data set, we measure perplexity, and as a proxy for segmentation quality, also mode classification F-score based on the segment features. So remember this practical definition of mode. The logic is, if mode groups melodies by similarity and you remember it that way, then segments that better capture how you remember should also make it easier to group melodies into modes. It's not the best of links, but it's something we can use, right? And it works. We get best segmentation so far in terms of mode classification. Also, when we run a monk simulation, so just learning melodies from a single manuscript, we still get state-of-the-art classification results. The perplexities are nice too. The baselines are between 30 and 300, so getting these numbers is nice. And importantly, the perplexities are correlated with the mode classification F-score, so this link between modality and memory now has some empirical legs to stand on. The segments that we find even are sort of more formulaic at the beginnings and ends of melodies, which fits really well with chant performance practice. But it's not syntonization. Despite all these nice properties, most of what we get is the one on top. The one on bottom is a rare example of something that looks like what was proposed in chant scholarship. So it's still a mystery, and come let us know what you think about this at the poster.
Next paper is IdolSongsJp Corpus, a multi-singer song corpus in the style of Japanese idol groups. The presenter will be Hitoshi Suda.
안녕하세요. I'm Hitoshi Suda from AIST Japan. Today, I introduce our new corpus, IdolSongsJp, a multi-singer song corpus in the style of Japanese idol groups. So this corpus consists of 15 newly composed Japanese multi-singer songs created by professional composers. We are sole copyright holders, so you may listen to the songs, you may use for research and for entertainment, and also you can create arrangements such as covers, parody lyrics, remixes, rearrangements, as long as you follow the license. So we designed for this corpus for 3 main goals. First, each song was produced very much like commercial releases in terms of mastering styles, loudness levels, the number of instruments, and the lyrical styles, and so on. And second, each song features multiple singers, so this corpus can be used for multi-singer MRR tasks such as singer separation, multi-pitch detection, and singer diarization. Third, this corpus has flexible license. For example, you may share these songs on web, so you can use for subjective evaluation of web-based music listening interfaces. So now I play 3 out of 15 songs. Please enjoy. コメディスライス深い立てます今日ダンスが教師愛好人になしもっと広きステージ広き広き広き広き広き俺だけ見てろよ Let's get up, we are free 向かい風が僕ら阻んでもこの翼 Intuitively there's nothing wrong with this 夢は終わらない I'm always by your side 俺とはテンションランドワンやることなすことマジハイパワー引きつける Oh baby, gap is the living or gap is the dying 君と共に息をつけてこれるんだぜ You be fighters to me 君は君でしょ正解はどこにもないいつも自分だけのワンチョイス選択するの Baby も今のすぐスタン止められない絶対ここで決めていけ So you will hear a wide range of music styles typical in Japanese idol group music. This slide shows what audio files included in this corpus. This corpus includes final tracks mastered with different loudness levels, -7 LUFS and -9 LUFS. And this corpus also includes dry vocal tracks and instrumental stems, so you can use this corpus for music source separation and singing voice synthesis. Also, this corpus has instrumental versions and solo singing versions that combines instrumental tracks and each singer's solo tracks, so you can use this corpus as a parallel dataset of solo singing. Finally, again, we constructed IdolSongsJp. This corpus can be available and on Hugging Face, so please check it out. 감사합니다.
Nice. Okay, so the next paper is titled GOAT, a large dataset of paired guitar audio recordings and the tablatures. The presenter is Jackson Loth.
Hi, I'm Jack, and I'm going to be talking about GOAT, which is our new guitar dataset. So GOAT is the Guitar on Audio and Tablatures dataset. It contains a little under 6 hours of audio with full MIDI annotations and also full guitar tablature annotations. All of the guitar recordings are DI, so the raw output of the electric guitar, which allows for a lot of tonal flexibility. It has multiple guitars and guitarists, and we also provide around 30 hours of audio rendered with our data augmentation strategy, which is basically just rendering this with a bunch of different guitar amplifiers. So the motivation behind this dataset was to have a dataset with tablatures as the annotation, because guitar tablatures are a pretty standardized representation, and within the guitar community, they're very popular, they're very easy to understand and to make, and they capture a lot of playing techniques very easily. We also wanted the dataset to have the guitar DI, which allows us to basically augment the data very easily by rendering it with different signal chains, so different kinds of guitar amplifiers and different kinds of pedals and things like that. In order to get the data, for about half the data, we actually purchased it from 2 content creators who already had this kind of paired audio and tablature data that they were using for educational content. And then the other half, we recorded ourselves using community-sourced tablatures. And so we have standard tuning and non-standard tuning in the tracks, and all the tablatures are in the Guitar Pro format, which is a popular format with guitarists. However, because MIDI is also a popular annotation format to use, we also converted all the tablatures to MIDI, and we used a fine alignment procedure to more closely align the MIDI note onsets with the audio note onsets. For this data augmentation with the amplifiers, if we think about how the signal chain works with amplifying electric guitar, you have the DI, which is just the output of the guitar, an amplifier, which is going to add distortion, and then a speaker cabinet, which basically just shapes the final frequency curve, which is very easily modeled using impulse responses. So in order to do the amplifier parts, we use the Neural Amp Modeler, which is basically an open source digital amplifier modeling software. And we scraped around 7,000 profiles for this software from their website, where the profiles are basically just a snapshot of some kind of amplifier that someone has made. And so using this and speaker cabinet IRs, we're able to basically take some audio and then use a random profile and a random impulse response and even an optional room reverb and get a very, very large amount of tone variety and realistic tone variety. So I'm going to skip past these. If you want to see the statistics, just come to the poster. As far as use cases for this, we think this could be great for a lot of different MIR tasks. For example, transcription, synthesis, playing technique identification, distortion removal, and I hope you guys can probably think of a lot more. Also to evaluate the usefulness of the dataset, we use some transcription experiments. So we have a MIDI model that we trained that was able to get competitive MIDI transcription results and also showed the effectiveness of this amplifier augmentation strategy. We also messed around a little bit with direct tablature transcription, which did not really work very well, but kind of showed promise, and we think this is a really good direction for future work. Here's just some MIDI results. Again, come to the poster if you want to talk about it. But anyway, thank you. If you want to check out the data set, just use this QR code. And thanks.
Next paper is Stage, Steamed Accompaniment Generation through Prefix-Based Conditioning. The presenter is Giorgio Strano.
Thank you. Hello, ISMIR. I am Giorgio from the Gladia Research Lab in Rome, and this is a brief introduction to Stage, our approach for single-stem accompaniment generation. So as you all guys know, large language models, pre-trained ones, are very powerful, yet very raw modelers of sequences. They just predict the next token. And they only really shine once they're fine-tuned through either supervised instruction tuning or reinforcement learning to solve a specific task, such as holding a conversation or programming for you or solving math problems. Now, this idea for music is still largely underexplored. The main goal of this paper is to understand whether we can exploit the immense raw predictive power of a pre-trained autoregressive audio model such as MusicGen and fine-tune it to solve a specific task. The task we decided to solve was accompaniment generation. Given a musical context as an input, we want to generate a new stem that fits well with it. And we tried many different ways to solve this problem, but what we found to work vastly better than anything else is something that's actually quite similar to how large language models are fine-tuned. We treat accompaniment generation as a question-answering task. And therefore, we can fine-tune the model on pairs in which the context is a question and the target stem is the answer. We do that by adding a new token to the model's vocabulary. Let's call it a context token, which tells the model where in the input sequence there's the context and where there's the actual sequence to be modeled. And importantly, this lets the model process the conditioning through self-attention, which we consistently found to be much stronger than cross-attention whenever there was a need for a precise temporal matching between the input and the conditioning. And this is crucial. And this very simple approach allowed us to extract performance from music that vastly surpasses any open source accompaniment generation model, even having a fraction of the parameters of many other baselines. And in fact, I wanted to specify that MusicGen was not even able to generate a single stem track prior to this fine-tuning. So what we find very interesting is that training one model per target instrument is highly parameter efficient. And we can also see in modern mixture of expert language models that in general, this idea of compartmentalizing knowledge between the parameters of the model can be very effective. In this case, even training a different model for each target instrument would still use less parameters overall than a combined model that can generate every instrument. Now, we also integrated pairs in the training set in which the context is replaced with a simple metronome track. Now, the obvious consequence is that now the model can follow a metronome, which is clearly useful. But what's less obvious and more interesting is that this improved performance of the model over many other metrics in accompaniment generation, and not only metrics that are strictly related to rhythmic alignment. So we think that this is very interesting and useful to keep in mind in the future, because by integrating samples that specifically model the basics and the foundational concepts of a task in the training set, then the model becomes biased towards these more foundational concepts, and therefore generalizes better in the more complex scenarios. So I'm going to leave you with a couple samples. This is a piano track taken from a held-out test set that the model has never seen before. And we're now going to listen to the generated drums for this track. As a last audio example, I'm going to leave you with a guitar riff. And these are the generated drums for this guitar riff. Everything is open source and open weights, and I can't wait to see you guys on the GitHub repo to try this model on extremely out of distribution data, because that's the most fun part. Thank you.
Next paper is do music source separation models preserve spatial information in binaural audios? The presenter would be Richard Nambala.
Close enough.
Sorry. How is
Nambala.
Oh, Nambala, sorry. Yeah.
Hello, everyone. Thanks for having me. My name is Richa. You might recognize me from the Slack. I like using emojis. I will be presenting my work, Do Music Source Separation Models Preserve Spatial Information in Binaural Audio, a collaboration with my co-authors, Professors Rudzinska and Fuentes at NYU. So for those of you who are not familiar with binaural audio, it's a two-channel spatial audio rendering technique that contains interaural cues that differ in time, level, and spectral content to simulate how a sound emanating from a source would be perceived by the human ear in a virtual space. Most often, we reproduce it on headphones, but it can also be reproduced on loudspeakers if you enable them with crosstalk cancellation. In order to record it, we use a binaural dummy head microphone, like my friend Fritz up here. I like to call him the ideal man because he's a very good listener. We can also synthesize binaural audio using a set of head-related transfer functions, or HRTFs, which capture the reflections of sound on our individual pinnae, or outer ears, and our bodies. So binaural source separation exists in the environmental and speech research communities under the task of target source extraction, which includes both the isolation of the source and its localization. However, this type of audio has not been used much in the MIR community despite its potential applications. Some of these applications include mixing virtual concerts for virtual and augmented reality. We can also enhance live musical experiences for differently abled listeners who are hearing impaired or neurodivergent. We can also take advantage of spatial information to improve the performance of downstream tasks by improving the clarity of separation. That begs the question, are the spatial characteristics of binaural musical signals preserved in the output of existing stereo MSS models? In order to investigate this, we needed data, so we synthesized a binaural version of MuseDB called Binaural NewsDB. It's created from the stems of MuseDB with the HRTFs from the SADI2 database. We applied some constraints on creating this data set, such as only placing sources in the frontal plane of the listener and not allowing sources to overlap. On the left, we have an overview of the synthesis pipeline. Angles were chosen randomly for each track, so it results in the random distribution on the right. And we evaluated our audio on 3 different models: Demux, Open Unmix, and Splitter. We specifically chose these ones for reproducibility and to allow for a comparison with the existing literature. We evaluated the results using these metrics. The first 3 are spatial metrics: the change in interaural time difference and level difference, the signal to spatial distortion ratio, and the last non-spatial metric is the signal to residual distortion ratio. For more information on the exact definition, please come to the poster. So overall, we found that the separation quality itself was fairly consistent across the stereo and binaural data sets, but there was a lot of spatial distortion in the binaural settings. In the binaural-based stems, we found that there were large deviations in the interaural time difference, and in the order of like hundreds of microseconds. And so even though they're microseconds, the just noticeable difference for ITD in humans is 10 microseconds, so that's a huge deviation. We also found that the ITD distorts more the farther the source is placed from the origin, so more to the left or right, which is not necessarily reflected in the energy ratio metrics. All in all, we found there is a considerable gap in model performance between the stereo and binaural settings. We have some plans to build upon this work in the future. First, we can take a look at the effects of using different source locations and measurements in the synthesis process, dive deeper into the metrics, and also evaluate new state-of-the-art models and train models on the binaural data. So if you're interested in listening to some of the examples, I encourage you to put on your best pair of headphones and scan the QR code. It's also on the poster. And I would also like to plug our late-breaking demo tomorrow that my colleague Yujin Kim prepared. So if you like source separation, K-pop, or me, you will pay him a visit. Thank you.
Cool. Next paper is estimating musical surprisal for an audio in autoregressive diffusion model noise spaces. The presenter is going to be Matthias Rose, BR.
Thanks. Very nice. Good pronunciation. So yeah, I'm here, Matthias, to introduce our work about estimating musical surprisal in audio using diffusion models. And it's work done in collaboration with Université Paris and the university in Johannes Kepler University. Yeah. So an important aspect of music composition is balancing redundancy or repetition and surprise. So if a material is too repetitive, it is experienced as unengaging, and therefore composers, they introduce surprise to keep listener engagement. So here is a simple melody, it's quite demonstrative, where an arpeggio is repeated 4 times. However, on the fourth occurrence, pitch is out of tonality and therefore surprising. So how can we model surprise? So basically we model the listener by an autoregressive model that predicts the continuation. Then we can start to ask questions about how surprising is the next musical event as given by its information content or negative log likelihood. Or we can also ask questions like how uncertain is the model at all as given by the entropy. So now to the diffusion model in audio, modeling in audio. So we basically take audio and encode it as a complex spectrogram and then use an autoencoder to get some latent representations. We then train an autoregressive transformer model, which is a diffusion model, simply predicting the next sequence in the sequence element. Then we use this complicated formula, which is an instantaneous change of variable, which basically allows you to predict the negative log likelihood of next sequence elements. And here was supposed to be a very nice animation, but I think I broke it. So instead, basically it just ends up being that you follow the probability flow ODE and do an additional numerical integration. So resulting in something like this. However, we also find out that you can actually also noise the data and solve this integral anywhere in the noise process, and you then get the information contents or surprise of noise data. So why would we want to use noise data? So we argue that, that the fine details are not as perceptually relevant as more coarse features. So when we noise, we remove some of these fine details but preserve the most important things. And this is also will be for you for next time. So let's instead jump to how the surprise estimates look like. So after returning to our example, we can now plot this surprise estimation in time. And what we see immediately is that indeed node onsets are represented with peaks, and repetitions are lowering our estimation of surprise. And when we have this out of tonality pitch, we have an even larger peak. Then we try the noised version where we noise the data, and we find that indeed it represents a more condensed version. In quantitative studies, we find that diffusion models, they basically outperform previous models, and that using this noising indeed improve our correlations with the other pitch surprisal estimation methods. And also we find that the information content aligned with segment boundaries, and that the resets, so introducing new material as a new musical segment is also giving spikes in this curve. So thank you for your attention, and please come and talk with me at the poster.
Next presentation is on video presentation titled Improving Neural Pitch Estimation with Sweep Kernels. I think the presenter would be David Martilla.
Hello ISMIR, my name is David Martilla. I'm a PhD student in AI and Music at Queen Mary, and I'll be presenting a paper Improving Neural Pitch Estimation with Swipe Kernels. Let's start with a quick look at Pesto, a self-supervised neural network architecture for pitch detection. This got the Best Paper Award at ISMIR 23, so probably quite a few people here have heard of it. This model takes CQT frames as input. The idea here is that both the CQT bins and the candidate pitches in the output distribution are evenly spaced on the log frequency scale. That means a pitch shift operation can be represented by simply transposing these vectors by some number of bins. And then Pesto teaches the model that a shift in the input should result in a shift in the output that exactly corresponds to the input shift. Let's also quickly get an intuition for the swipe algorithm. The core idea is to take a number of candidate pitches in your search range and generate these spectral kernels that are roughly based on the spectrum of an ideal sawtooth wave. So you get these decaying peaks at the harmonics of the candidate pitch. And to estimate the pitch of a frame of input audio, you simply correlate each of these kernels with the spectrum of the input frame. and this gives you a score for each of your candidate frequencies. And in this work, we'll treat these scores as an input feature to a neural network pitch detector. These scores are evenly spaced on a log scale like the CQT, but most importantly, they contain very explicit information about the audio frame's periodicity. So our hypothesis is that if we want to use these scores as input features instead of the CQT, we can make it easier for the network to learn what we want it to learn, which is exactly to give us the periodicity of an input signal. So here we're comparing the original pesto model with a modified version where we're using the swipe scores instead of the CQT as input. And here I just want to highlight two things. One is that the swipe algorithm on its own, just the DSP baseline in its original form, actually outperforms the original pesto model in these evaluation scenarios. And the other is that using swipe scores as input features actually allows us to drastically reduce the model size. Here we have a model that's just cut down to the final triplets layer, so it's basically just a single convolution operation. And it outperforms the original pesto model in 3 of the 4 cases. And it also gives a small improvement over the swipe baseline, so it seems to learn to reweight and refine the location of the swipe peaks a bit, maybe, but it's not a very big difference. So wrapping this up, what are the main takeaways of this work? Definitely check the baselines that you're comparing against. Make sure they're strong, maybe that you can reproduce the baseline results that previous literature is reporting. This is a pretty big point here because previous work on self-supervised pitch detection has very often used swipe as a baseline to compare against, but they reported much, much lower accuracy. So what we found here means that basically all of these previously proposed models don't actually really beat the baseline they're comparing against. And the other one, I think, is that in some cases, maybe you want to consider using handcrafted features as input to your neural networks, because that can make them more efficient if the features explicitly encode information that is relevant to your task. This is, of course, not a magic bullet. So in our case, we found that using swipe scores worked well for the self-supervised case that I've just presented. But we also tried supervised architectures with these scores as input, and it still worked pretty well overall, but we weren't seeing the same kind of state-of-the-art results. So if you have any questions, suggestions, or any other input on this, please get in touch. Thank you for listening, and enjoy the conference.
Next paper is Optical Music Recognition of Jazz List Sheets. The presenter is Juan Carlos Martinez Silvilla.
Hello, everyone. Thank you, Mr. Wang, for presenting me. Well, this is a work that it's been a collaboration between the Johannes Kepler University, the University of Salamanca, Spain, and also the University of Alicante. So I wanted to thank you all the co-authors, Patricia, Francesco, David, Jorge, and Gerhard Widmer. Well, what are jazz lead sheets? Well, these kind of scores are really special because they contain both the melody information and also the chord changes of the music. And this is really important because it also, in addition to this information, it opens up for the musicians to improvise. But we have a problem here, and it's that the musicians prefer to still use jazz fake books or the real book, or even if they are composing something, they prefer to write it down. That's why it is important to digitize the score, because they can be, scores can be corrected, adapted, or transcribed, or whatever for further tasks. And here it is where OMR takes the lead, because it's the way to do it. However, OMR has problems with these kind of scores, which are, first, the variability in the handwritten style of different authors, and also the recognition of the chord changes, which hasn't been really approached yet. So this is why we present the JMOS dataset, which expands for almost 300 pages of handwritten scores that are also aligned with their music XML and hand-kern encoding. We also provide the synthetic rendering both in jazz and classical font. And also, we really focused on cleaning and and designing a way of standardizing the chord encoding. Because as you may know, chords can be represented, the same chord can be represented in different ways. So we try to avoid that. And the other contribution of this work is the training and the design of a new OMR system to recognize just lead sheets. It works at line level, so first we need a pre-processing step to retrieve the relevant regions of the page. And yeah, it's an encoder-decoder with a connext encoder and a transformer decoder. We explore also different tokenization strategies at word level, medium level, and character level. And, well, these are the results measured by word error rate, character error rate, and line error rate. And as you can see, the best results were with the model pre-trained in other kinds of music that didn't have chords. And then we did let's say, a brief or little fine-tuning on handwritten scores of Jasmus, and then also synthetic scores, getting pretty good results at the medium tokenization level. So to end this presentation, I wanted to thank all the institutions from Spain that made possible gathering all these pages annotated by hand by all their students, either amateur or professional students. So, yeah, thank you very much, and hope I'll see you in the poster. Yeah, thank you.
Thank you. For the next paper, it's titled Human versus Machine, Comparing Selection Strategies in Active Learning for Optical Music Recognition. The presenter is Juan Pedro Martinez Astaso. Are your guys' name very close?
Hello everyone, my name is Juan Pedro Martínez Esteso from the Pattern Recognition Artificial Intelligence Group at the University of Alicante, and I'm going to present the work Human versus Machine, Comparing Selection Strategies in Active Learning for Optical Music Recognition. First, optical music recognition is the process which aims to transcribe the music scores into a digital format. And within this field, we can find we can apply the layout analysis, which aims to segment the music scores in several layers of information, such as symbols, lyrics, notes, or background. Today, the deep learning models have several limitations, such as they depend on large amount of label data, and also the annotation process is very time-consuming and highly labor-intensive. So what the solution we propose? We introduce an active learning framework with a fusion learning strategy for layout analysis. The methodology of our framework is illustrated in this figure. First, we start with a pool of unlabeled images. Then a patch selection strategy determines which patch from which image should be annotated. Then a human expert provides annotation for this patch, and it is added to the training set in order to retrain the model. And the result improves progressively. And this process is iteratively repeated until a criterion, and the stopping criteria is reached. And also we will focus in the patch selection stage where we'll compare the human selection against 4 random selection, automatic selection strategies, which are the random selection, sequential selection, intensity-based, and entropy-based selection. Regarding the experimental setup, we employed 3 common data sets using the literature of OMR. And each one has 4 layers of information, which are staffs, notes, text, and background. The model we employed is a fusion selectional autoencoder, which is an encoder-decoder architecture. And we incorporate a masking layer to ignore the annotated regions and an oversampling process to increase the patch variability. Also, we employed an annotation tool that we developed ourselves, and the metric that we employed is TIFF1 score. Now looking at the results, in this first graph, we can see the performance of the 5 human annotators. And we can observe that between the best and the worst, there is a notable variability, almost 20%. In the second graph, we compare the average result of the humans against the 4 selection automatic methods. And we can see that the best results are achieved by the entropy-based and the ink-based selection method. This table shows the results when training with samples ranging from 1 to 32. And also we can see that the automatic selection methods surpass the human annotators. And also in the last row, we can see the time required by human annotators to annotate the samples. And we can see that just for annotated 32 samples, it was required more than 4 hours. And finally, this figure shows some examples of patchy selective for the text layer. And at first sight, we can see that all of them seems appropriate, but the results previously analyzed shows that the features in which humans focus may not be the most suitable for training the neural networks. To conclude, we can say that automatic methods outperform manual strategies. The human annotation is more inconsistent, and I think it can vary depending on each annotator. And automatic active learning strategies can optimize optical musical recognition and workflow. And that's all. Thank you for your attention, and we can meet in the poster session. Thank you.
Next paper is assessing alignments of audio representation with timbre similarity ratings. The presenter is Haokun Tian.
Thanks for the introduction. Hello, ISMIR. My name is Haokun Tian. I'm happy to present you this work assessing the alignment of audio representations with timbre similarity ratings. This one is also about human versus machine. So our focus is on perceptual distances between timbre. You can think of it as a function that takes 2 instrument samples as input and gives a distance value that reflects how different they sound perceptually. The samples share the same pitch, loudness, and duration, so the only difference is timbre. By adding more and more sounds, we can have a similarity matrix that shows the perceptual distances for each pair of samples. For data, we have existing human annotations from past psychoacoustical studies. Altogether, there are 21 tiny data sets. 3 of them are plotted here. In total, that's more than 2,000 ratings across 334 audio samples. In this work, we test how well today's timbre models align with human ratings. The workflow is straightforward. We compute distances between audio embeddings, put them in a similarity matrix, then compare the difference between the predicted similarity matrix with the human annotated one. We evaluate both the absolute value and rankings. So our experiments cover 18 audio representations, 2 approaches for lines alignment, 2 distance functions, and 3 evaluation metrics, with 1 focusing on absolute values and the other 2 on ranking. Apart from traditional timbre features, we introduce a new family of representation called style embeddings. So these embeddings were originally proposed for image style transfer. And instead of representing the style of an image, we apply them to represent the timbre of an instrumental sound. Style embeddings can be extracted from any CNNs or transformers where the input data is internally represented as feature maps with channel and spatial dimensions. We experimented with 2 types of style embeddings. Both of them are computed from multiple intermediate feature maps in deep neural nets. And now let's look at the results. First, some codecs are not good at this task because they're too localized for retrieving a global difference. In comparison, music to latent also has audio codecs has a lower frame rate and does a better job, and is good at predicting absolute values. MFCC is competitive, and remarkably, style embeddings are effective. The best performing representation comes from the Huang style embedding extracted from a clap model. And the style embeddings from both clap and the newly trained sound matching model outperform their base representations. Thank you so much.
Next paper is titled Simple and Effective Semantic Song Segmentation, and the presenter is going to be Filip Krozheniowski. Yeah, I've been practicing how to pronounce your name for 3 years since I first met you. Hope I get it right this time.
All right, hello everybody. My name is Philip, and I'm presenting on behalf of Richard and myself our work on simple and effective semantic song segmentation. So what is song segmentation? Basically the goal is, you already know of course, but I have to explain it. You input an audio, you put it through a model, and you get song segments which are labeled semantically, like intro, verse, and chorus. And this is like a very long-standing task, of course, in the ISMIR community. This is just a bunch of deep learning models that were presented here in the last couple of years. And our focus here is on presenting a new model that is trained in a supervised manner, and it predicts semantic labels, so like intro, chorus, verse, and not like only A prime, like similarity-based labels. So as I said, the first contribution is in a new state-of-the-art model, and we also in the paper discuss certain considerations regarding evaluation when it comes to data and metrics, and also we introduce or suggest to use a new data set for evaluation to clear up some of the problems the evaluations have. But in this presentation, I'm going to focus on the model itself. So our model is basically an all-convolutional network that takes as input 3 input features. One is the log spectrogram, and the other 2 are self-similarity lag matrices. That's right, feature engineering is back. And we input these to the model through 3 three-layer convolutional front ends. The outputs of these front ends are concatenated and put through 11 TCN blocks to capture long-term dependencies. And finally, we put them through 2 frame-wise prediction heads. One predicts the segment boundaries and the other labels, as introduced by Zhujiang Wang. And that's it. We train it in a supervised manner by using these data sets. Harmonics dataset, RWC Pop, Beatles, and Salami and Queen. For Beatles, we actually use the original annotations, and for Salami, we use both annotations for a track if they're available. We train that in 8-fold cross-validation for 100,000 iterations using a batch size of 1, and use RADAM with look-ahead and stochastic weight averaging to improve the generalization. All right, so let's evaluate that model. We look at the data sets, and the problem is that there's data set overlap. Salami is a data set comprised of many different data sets. So for example, 20% of RWC Pop is actually in Salami, and we have another overlap with the Beatles. In this work, we remove these duplicates, but however, if you look at cross-dataset evaluations, you always have to keep in mind that there might be a significant train-test overlap, and therefore the results might be inflated. To enable a more clean evaluation, we actually propose to use a new dataset or an old dataset, the Mitchell-Bilbert dataset. It has been used for other studies in MIR, but to our knowledge, it was not used for song segmentation. Here we removed duplicates within the dataset and also overlap with other datasets. The nice thing now is that we can have very clean evaluation because no model was ever trained on this data. The problem is that we can only compare with open weight and open source models. So that's what we did. Here I'm focusing only on this data set. In the paper we have evaluations of other data sets as well. And we see that compared to the Gorilla and Schlüter model from 2015 to Buisson 2024 and the all-in-one model from 2023, our model achieves state-of-the-art results in as well as segment boundaries. So we use F1 at 0.5 seconds. But also on label-related metrics like NCE-F1 and label accuracy. Yeah, that's pretty much it. See you at the poster. We presented a new state-of-the-art model. Let's discuss the evaluation at the poster, and yeah, see you there. Thank you.
Cool. Nice paper is called Musical, a community-driven framework for assessing openness in music generative AI. The presenter is Rosaire Roca. Is that right?
Thank you, yeah. No worries. Well, hello, ISMIR. I'm Rosé, and today I'll be presenting our new article, Musical, a community-driven framework for assessing openness in music generative AI, done in collaboration with my co-authors at the Music Technology Group at Universitat Pompeu Fabra. So this work originated from multiple discussions around the concept of openness, where we have been considering questions such as, what is an open model, or what does it mean actually to be open, which also led us to question, how can we actually assess openness in music generative models? So for this presentation, I'll be focusing on this last question. And the thing is that when we started wondering this, we realized that openness is rather a multidimensional concept rather than a binary one. And the thing is that the proper definition must consider different aspects of the model, but also balance them with practical considerations, such as like data privacy or intellectual property, which are particularly sensible in the music domain. So aligned with this, there are some initiatives that propose structured gradient-based frameworks to evaluate openness. Among them, we found an interesting evidence-based criteria to assess openness in LLMs, which characterizes for being composite, meaning that it has multiple dimensions, but also that they are graded, so each dimension may have different degrees of openness. The thing is, does it work for the music domain? Not really. The thing is that some of the categories are really LLM specific and they don't capture music nuances, so it needs an adaptation. We did the first preliminary adaptation of this framework. However, we didn't want this to be our own perspective. We wanted the MIR's community's perspective, so your opinion. And that's why we did a survey that actually got over 100 responses. So if you participated, thank you. Because with all of this, we were able to tailor the framework into the music domain. So what we did was that from the received feedback, we were looking for common patterns, agreements and disagreements of all the comments that we got. And in the end, we adjusted the reference definitions, we renamed categories, and also included new categories that are suitable to our field. And the other thing that we also asked in that survey was the relevance of each category. So participants rated the relevance from a scale from 1 to 5. And we split the framework then into two categories. So essential categories are considered critical for assessing openness, and then the desirables are those ones that add value but are not critical for openness. So with all of this, we ended up with the Music Generative OpenAI framework, what we now call the MUSGA framework. And MUSGA characterizes for having 13 categories, 8 essential and 5 nice to have, or desirable categories. And the thing is that essential categories follow a 3-level graded scale, so they can be closed, partial, or fully open. And instead, desirable categories are binary. They are available or they are not, so they have like star, like if you're a kid. And then these allowed us to get to this openness leaderboard where we analyze 16 state-of-the-art open models and ranging a bunch of architectures, but everything is available in our in our website, where you will find a description of the table, how it works. Also, when you go through each one of them, you will find the justification. When you click, you are redirected to the model, but if you click to the institution, you are redirected to the model's first page. And sorry, that was no. I don't know what's happening. Well, anyway, if you would like to know more on how to contribute, because we are super looking forward for everybody to share their model, so we can have like a summary of all the models available, you can scan the QR code, go to our GitHub repo, and yeah, hopefully I'll see you in the poster session.
Nice framework. Next presentation is an video presentation. She's titled The Potential of Unsupervised Induction of Harmonic Syntax for Jazz. I think the presenter will be Ruben.
Hi everyone, I'm Ruben Kertevels, and I will present our paper called The Potential of Unsupervised Induction of Harmonic Syntax for Jazz. Harmony in music, in the form of chord symbols, can be represented with parse trees, as you can see on the right. Such a parse tree groups together chords according to their relations. For example, a dominant chord followed by its tonic will be grouped together. And this parse tree shows the structure of the harmony of a music piece. At the same time, these harmonic trees can be parsed by a probabilistic context-free grammar, of which the rule probabilities are parameterized by a neural network. We use neural parameterization of those rules that has been proposed for unsupervised parsing language, and we adapt it to sequences of chord symbols. And important to note is that this probabilistic context-free grammar is trained by maximum likelihood on the raw chord sequences, so we do not need tree annotations for training, which enables us to use much larger corpora of chord symbols. Our results show that the predicted parse trees overlap in many cases with annotated parse trees. We evaluate on annotated parse trees of another existing smaller corpus. For example, the model successfully finds the 251 patterns here, but it misses that the F minor chord is likely to be a predominant chord to the dominant G, just like the half diminished is. Thank you for listening, and if you are interested to know more, feel free to read our paper or check out our GitHub repository.
Next presentation is MIRIX 2025. It's going to present by the MIRIX team. Junye Jiang, right?
Yeah.
Okay.
So, hello everyone. Welcome to the report of this year's MIRIX competition. I'm actually very happy that the MIRIX competition can be included in this year's oral session, because also the session topics is very related to the MIRIX itself. I'm Junyan Jiang from the Future MIRIX team. I want to start with some facts about MIRIX for people who are not familiar with it. MIRIX stands for Music Information Retrieval Evaluation Exchange. This is a competition platform hosted by the International Music Information Retrieval Systems Evaluation Lab at UIUC from 2005, but was interrupted in 2021 due to multiple reasons. We restarted from 2024 and it is now jointly hosted by the Future Mirrors team and UIUC. Below is the main website for the Mirrors wiki page. Mirrors hosts a lot of music information retrieval-related challenges, including music analysis tasks like chord recognition, genre transcription, or genre classification. There are also some practical applications like music retrieval and defect detection. This is a cloud tag of all the Mirrors tasks ever hosted. I also participated in multiple tasks many years ago, including audio fingerprinting, chord estimation, and key estimation. To me, Mirrors is a very useful platform to guide me into the field of music information retrieval. And now I'm happy to be one of the organizer team and the task captain for multiple tasks. Many of you know that the Mirrors competition paused for 3 years. When we restarted Mirrors in 2024, we had two thoughts. The first is to gradually bring back traditional tasks. But to make the platform thrive, we also introduced modern, cutting-edge challenges to Mirrors. Here's the image for the number of Mirrors participants and submissions each year. So you can see that there's a decline before 2020, followed by a 3-year pause. We are currently restarting Mirrors with a limited scale, but we'll gradually expand it in the future. Participants also achieved some new records in these 2 years, including mu cross-cover in cover sound detection and kg Apollo beats in audio beat tracking for this year. For the complete result, please refer to the Mirrors website or see our poster. We will start next year's Mirrors by a new round of call for challenges. We invite all of you to propose challenges that are related to ISMIR. As a long-term goal, there are 3 objectives we want to achieve. The first is to make Mirrors an open evaluation platform that is accessible to everyone. For example, a new undergrad student might use Mirrors to make oneself familiar with certain tasks. Second, we also want to promote standardized benchmark in several music information retrieval tasks. We have noticed many issues like inconsistent evaluation metrics and inconsistent data split in recent works, and also like the data contamination presented by multiple speakers before me, like by the presenter Phillips. We hope task captains can open source and promote standardized evaluation benchmarks to avoid these problems. The last thing is that we want Mirrors to stay aligned with emerging research areas, because you all know we are currently in a rapidly changing world, and the research focus in MR might change every year. Thank you for your attention. I would like to express my thanks to all organizers, task captains, and participants for their contributions, as well as the dataset providers who made these challenges possible. To learn more details, please stop by our Mirrors poster in Wednesday afternoon and Thursday's late-breaking demo. Thank you.
Okay, I think that ends the section, so we can move to the poster.